2 billion global members. Yeah. So these are some of the offices that we have all over the world. Our Singapore office serves as the Asia Pacific headquarters, which houses a few companies as well, like Global Ad Tech Division, where we are from. There's also Rakuten Viki, Travel, uh, Symphony, to name a few. Yeah. So just now I mentioned that we come from the Global Ad Tech Division. So that's Rakuten's advertising business, where the ad agency would help to create and manage the ad campaigns for the various brands and companies. And we, as GATD, will support by developing and maintaining the tech for this advertising business. So when a company comes or merchant comes to us and spends on an advertising campaign, it's important for us to see how effective is the ad campaign. Like once they have targeted a certain audience and spent a certain amount of money for the ad campaign, we need to track how effective it is. And that is through tracking the users through event logs. Let's say we have served some advertisements to a user, right? Like say when it's served, whether the user has seen it, that would constitute an impression log. We'll want to know at which timestamp did the user see it, on which device, location, which user ID, etc. So this would be the impression event log. And if the user has clicked on it, then it would generate a click log, which we will also record as well. Otherwise, if it's a video ad, whether the users have watched it, then there will be a video watch log. And subsequently, if the user wants to buy something, there's the add to cart and purchase log. Yeah. So if the user buys something and before that the user has interacted with our advertisement, let's say through a click, we will try to pair them up together into a conversion, right? So this would help us understand which ad actually led to the purchase itself. So this would also help us to measure the effectiveness of an ad campaign. So all these event logs and data would be sent to our system for processing. And our system will transform, normalize it to make sure that the logs coming from the different ad services, be it like search ads, banner ads, mail ads, will be comparable with each other, right? So let me give you a very high level intro to our system. So a very brief one only. So our system is a hybrid of on-prem and GCP cloud infrastructure, right? As we are in the process of migrating to the cloud. On the left, we have our data sources that are coming from the ad delivery servers, which are mainly located on-prem. And our data warehouse and also the some of the architecture like PubSub, Dataflow are actually located in the cloud. Yeah, where the downstream consumers like the CV pairing application and downstream consumers for reporting analytics will consume from a data warehouse, which is on the cloud. Yeah, so when a user interacts with the advertisement, the ad delivery server will generate a log, be it an impression or a click log. Then it will be sent to the Kafka topic as a raw log, right? So purchase logs will be coming from the transactional DBs from another application. Then we will process via our data streaming pipeline in real time and send to PubSub for the downstream CV pairing, right? For the data that do not have any real-time applications, the app delivery servers will also write to a persistent storage Hadoop file system, and we have hourly batches that would process this data, and all of this would actually go into our data warehouse, which is based on GCS and BigQuery. Yeah, so I hope this gives you a good background about our system on a very high level. So today we have my colleague Satana, who will talk more about the data streaming pipeline that is on the top part to do the real-time processing. And then Raymond and I will share more on the data warehousing part down below. So maybe let me pass the time over to Satana to share on the data streaming part. Satana, please.
Thank you, Mankit. Hi all. I once again welcome you all for this data engineering meetup. So today I will be presenting on data streaming and monitoring. So think of all the data that your organization produces, like Rakuten, like the e-commerce organization will be producing so much website clicks, impression, and other logs, and some of the financial transactions in the banking sectors. So what if you could process all this millions of data and you can analyze the data and make some real-time decisions? That's the power of data streaming. Okay, so what is data streaming? Actually, we can process the data in batch as well as the streaming. What is batch? Batch process collects the data and process them in the discrete sets as scheduled intervals, like a reservoir. You know reservoir, where the water is stored and it's being consumed whenever it's needed. And what is streaming? Streaming actually it's the continuous ingestion, processing, and analyzing of the data with minimal latency. Think it of as a river, like the flowing water. So there are some key characteristics to this data streaming. First one would be unbounded data. Think of faucet. When you open the faucet, there would be continuous flow of water. So here in the data streaming, there will be unbounded data set flowing in. And the low latency, time is very critical. So when a data is being produced to it's consumed, there should be the minimal lag. There should not be much latency. And then the real-time processing. Once and ever we get the data, we should be able to process and do some transformations and analyze the data. Then the fault tolerance. Even if any component of the system goes down, still we should make sure of the data flow and there should not be data loss or the downtime. And then now we know about the data streaming, but where actually we are applying this data streaming in real life? Actually, we are using this data streaming from our coffee industry to the outer space. So the first example would be the Starbucks, where they use the data streaming for predicting the coffee demands to optimize the staffing levels and the inventory management. They can predict the future demand. Let's say if it is tomorrow's the hot day, there could be a big demand for the iced coffee, and then they can manage their inventory accordingly. And next would be catching credit card fraud. The banking sector uses the data streaming to study the user spending pattern. So let's say if there is a transaction history happening in some foreign country where the user is supposed to be in the hometown, and they could catch that fraud in the real time and they could prevent the transaction. And next would be monitoring rocket launch. So when a rocket is being launched, there will be n number of parameters to be monitored, from the engine temperature to the fuel pressure, and there would be many anomalies that needs to be detected and make a critical decision in the real time. Then comes our favorite streaming platform, Netflix. Netflix uses the data streaming to personalize our video recommendation and optimizing the video streaming quality so that they can keep us addicted. Next, now we know what is data streaming and where it's being used. But what actually involves inside the data streaming? So I said data streaming is the continuous flow of data. So there has to be some system that ingests the data. So first is the data source and ingestion. So this layer focuses on capturing the data from various sources. The famous technology for this would be Apache Kafka, Pulsar, and other cloud-based message queues. Next is streaming processing engine. So we got the data. What do we do with it? We process it, we analyze the trend and all that. So for that, we use the streaming applications in real time. And the famous technologies would be Apache Flink, Apache Spark Streaming, Apache Storm, and other cloud-based services. And then after processing the data, we have to store it somewhere. So there comes the data storage and management. We process the data and it can be stored in various databases like the NoSQL databases, time series databases, and even GCS. Then we have stored the data, but that's just raw data. Then comes our visualization and analysis platform where we can create a graph with that data. So there comes our tools like Grafana, Kibana, Tableau, where it will show you the trend in the dashboard and you can make the decisions accordingly. Okay, so now for the first technology, the data streaming platform, Kafka. So I'm talking about Kafka because we inside Ultra, we use the Kafka. So what is Kafka? Kafka is a high throughput, fault tolerant distributed system designed to support the streaming applications. Kafka can handle the continuous stream of data from multiple sources, making it ideal for the data streaming. But why Kafka? Kafka has many attractive features. So first one is the scalability. It has number of servers. It can scale up and scale down according to the traffic. And then the high throughput. It can process millions of record within a second. And then the fault tolerance. Even if some of the servers goes down, it can use other servers to maintain the data quality and prevent the data loss. Then the real-time processing. It can support the transformations and the processing of the data in the real time. So this is like a simple illustration of how Kafka works. So before going into the example, there are some of the terms which you can see, like producers, consumers, zookeepers, broker. Producer, as the name indicates, it produces the message. And consumers are the ones that consuming the message. And in the middle layer, you see the brokers. Those are the services that transfers the messages. And the zookeeper, think it like a principal who maintains all the servers. It will check which server is up, which server is down. And if any server is down, it will help to bring in the other servers. So there is an example. Like when you read or write data to Kafka, you treat it as an event. So here is an example where Alice has transferred Bob some dollars, and there is the event timestamp when it happened. So when it's being published to Kafka, there is this three important fields. One is key, another is value, and another one is the event timestamp. So key is Alice here. So she made some transaction to Bob. That would be the value of the key, and then the event timestamp when the transaction has occurred. Okay, so now Kafka, we are running this in our cluster, but as we are migrating to cloud, we have adapted PubSub. PubSub is very similar to Kafka, but it is maintained within the Google Cloud ecosystem. As you can see, the key features almost match to Kafka, but the exceptional one would be the global scalability. As it is within the Google Cloud ecosystem, we can maintain it in the different regions. And the example of PubSub would be similar. Like we had producers and consumers in Kafka, we have publishers and subscribers here. So the publishers would publish the message to some topic, and the subscriber would consume the message from that topic. So what is topic here? Think a library. So there would be different genres, and the books are arranged according to the genres, right? So topics are like genres. You will be publishing the messages to the topics, and only the subscribed consumers can consume those messages. Like if it is fictional, you go there and get the fictional books. Okay, so now we have seen some examples for the data streaming platform. Now comes the streaming application. So I have again taken Flink because we use it in our Ultra system. So what is Flink? Flink is just a streaming application that can process and perform transformations, filtering on that millions of record produced by the Kafka. So Flink easily maintains very large application state. And some of the Flink capabilities are like the correctness guarantee. So there is a feature in the Flink that's called checkpoint. Let's say the Flink is running. It will be creating the checkpoints. And if there is any, the application crashed, it would refer to the previous checkpoint so that it makes sure that all the messages are consumed at least once. Then there is layered APIs where you can perform various operations like processing, analyzing, filtering, transformations, and everything. Then there is operational focus and the scalability, like you can scale up, scale down, and then the performance. Like it supports the low latency, high throughput, and operational computation. Yeah. And in the operational focus, there is the third point called save point. Save point is very similar to checkpoint, where Flink itself creates the snapshots. But save point is like the snapshot created by the user. Let's say if you want to restart the application because you made some configuration change, then you will be creating the save point and you will be using that save point as a start to again restart your application. So it provides that flexibility to you without any data loss. Okay, next the integration. So we have talked about Kafka, PubSub, Flink, but how do they integrate? This is a simple illustration of how they integrate. So here the messages are produced in the Kafka, processed in the Flink, and published to some of the databases. So when the messages are processed in the Flink, it can either be published back to Kafka or stored in the databases. Same to the Flink, PubSub. It can connect with the PubSub source and it can publish back the message back to the PubSub or to the GCS. Okay. So now we have saw all the good parts of streaming. But is streaming is really will be working likewise? No, things can go wrong. So here are the few things that we have faced inside our Ultra while using Kafka and Flink. So first is the data loss. Kafka broker failures. So even though there are some zookeepers where the servers go down and they step in, but still there can be Kafka broker failures, network issues, and the consumer errors. Then the data duplications. Even though we have the checkpoint and save point, sometimes the Flink might consume the message twice, and then there will be the data duplication. Then the latency spikes. The brokers might be overloaded. The consumer might have the slow consuming rate, so the end-to-end latency will be high. And then the back pressure. Producers overwhelm the consumers. Producing rate might be high, but not the consuming rate. Then the schema evolution issues. Let's say you are reading a data with a particular schema. What if invalid schema comes in? Then the server might crash. But how do we mitigate this? How are we going to overcome? That's where we monitor our systems. So why do we monitor? We proactive problem detection, identify the issues before they impact the users, and then performance optimization. So when you know the servers are not enough, you step in and optimize and take the measures to optimize the performance. Then the capacity planning, anticipate the future resource needs. Let's say we have the sales in our Rakuten where we predict there could be more traffic in our service. So you anticipate that and increase your capacity. Then we troubleshoot quickly, diagnose and resolve the problems. Then here are some of the metrics that we monitor in Kafka. One is broker metrics, like how much is the CPU utilization, other things, and the topic metrics, like how many messages comes in, what's the latency and all that. And then the consumer metrics, how many messages are being consumed if there is any lag in the consumer. And producer metrics is same. Is there any lag in the producer or how many messages is being produced? So to monitor all these metrics, below are the tools that we use: Prometheus, Grafana, Kafka Manager, and the Datadog. So here is how we do it within the Ultra. So first one is the Kafka, where data is produced. Then we process it in the Flink streaming. Then we produce the consumed logs to the Prometheus. And also we produce the raw logs from Kafka to the Prometheus. Prometheus is just the time-based database. It would get the logs and store it according to the time. And then we build the Grafana dashboard, which consumes this Prometheus data and gives you the visualization of the incoming topics and the how much message is consumed and all that. Okay, so here are some of the monitoring strategies that we follow in our team. So first, clearly set your SLAs and SLOs. Talk to your stakeholders, know what they need, and then set your SLOs. Because as you saw, there could be a data loss, there could be a server downtime. So set your SLAs and SLOs accordingly. And establish baseline metrics. Like not all the metrics are important, but some are really important. So choose accordingly. And set meaningful alerts. You no need to be overwhelmed by all the alerts. You can set low priority alerts, high priority alerts as well. And automate remediation. You no need, not all the applications would need human intervention to restart it. There are some systems available to restart the application. And then practice incident response. Always have a plan when an incident happens. So Monet, as I said, there are some systems which help with the application restart. Monet is one of them. So you can set intervals of automatically restarting the application if it is down. You can set the intervals, like check the application status every 5 minutes. Then it would be checking it. If it could not retrieve the application status, Monet will step in and restart. And these are some of the futures of data streaming, like the cloud migration. As I informed earlier, we are also migrating to cloud. We are using PubSub and other GCP services. And then the AI powered. The Flink application might get optimized in the future with very minimal latency and then the increased throughput and all that. And the AI might take the decision on the data that it has got. And to the summary, so far we have seen about the data streaming platform and the processing engines. But if you are building the data streaming pipeline, please remember that you should be very careful in choosing your tools and build a resilient architecture. Yeah, thank you. I will hand it over to Mankit for the data warehousing part.
Oh. Yeah, hi. Thanks, Atana. My name is Raymond, and I'll be talking more about our data warehouse. Yeah. So I think what she covered so far is more on the streaming pipeline and the pub sub. So we have some background on where the data is coming from, upstream data stakeholders that we have. But the rest of the platform actually is where we store the data or we have our warehousing going on. So let's get into that. So the first stage is where the data source or data ingestion is happening. Data ingestion pubs up mostly, and GCS here is also serving as our incoming data source from upstream stakeholders. So after we have ingested all this data, we have processing layer here. So we use Dataflow, Dataproc to do most of our data processing. If you look at the top layer, actually, that's the real-time streaming. So Dataflow is streaming data in real time, whereas the bottom layer is more on the batch processing. So we use Spark jobs on Dataproc to actually do batch processing. And both of these processing actually writes back to our data warehouse, which is we're using GCS plus BigQuery here. So these are the three kind of steps that goes on on our GCS infra. And yeah, so let's dive into them one by one. Some of the tools are what's going on. So Dataflow is, like I mentioned, is real time. Its main job is actually to do the partitioning and some normalization of our logs. Partitions are important to us because we run queries on these partitions. So we partition by date, time, or hour, so that if you want to run queries, we can do some filtering based on these partitions. Dataflow is also responsible for handling any validations. So if there's invalid logs, we want to route them separately. We want to handle them separately. And yeah, so these are just an overview of we consume from PubSub, Dataflow processes it, writes to GCS. Along this journey of the migration, we had lots of things that we have to configure or tweak. These are two main points that actually I think is worth bringing up. So worker count and writing parallelism. So worker count is we want to have multiple workers processing the data. So the more number of workers we have, there's higher throughput and more data being normalized and processed. But along with that, actually, we also have the consideration on budget limits. Hence, we have a min and max threshold on how many workers we want. In super sale periods for us as an e-commerce business, the times where we have high traffic spikes, lots of clicks, lots of purchases, lots of views, and so on. So we want to make sure that our workers are able to adjust accordingly, but they don't exceed our maximum threshold. We don't want our budgets to be overrun too fast during super sale periods. So yeah, auto scaling is in place for worker counts. And then for writing parallelism, so you can process a lot of data using workers, but you also need to be able to write this data equally as fast. And to be able to do that, you need to be able to tweak or scale your writing parallelism. So this is another thing that we have been tweaking as we notice our servers have more and more load. So we increase our parallelism on the writing side. So together, parallelism and worker count is able to handle spikes in our data and work appropriately. So yeah, GCS is where we store our data, is a big part of our warehouse. When we were setting up this on the cloud, a couple of things we were actually looking into was the storage class. There's standard, nearline, co-line. So it's all about how frequently you want to access this data. If you use standard, it's the most expensive. And then different locations that we have to consider. So there's single region, dual region, multi-region. And this is more about our availability considerations for our data. And a lot of our SLAs and SLOs, we discuss how our availability is affected to our stakeholders. Access control is another one because we are a central data platform for Rakuten, and then there's people accessing our data that is normalized. So we want to make sure that we have the correct access levels for each of the stakeholders consuming our data and reports. Lastly, the storage period. So again, in the SLAs and SLOs that we discuss with our stakeholders, we need to ensure that there's some agreement on how long we will store their normalized data. We don't do it indefinitely. Typically, maybe 2 years, we store the data, and then this is something that we have to tweak as well. So just a high-level overview of the kind of buckets we had in plan. So we had one for hot data and one for cold data. So initially, we thought of, okay, we'll have one for standard storage class, where these files are accessed very frequently. So we need to be able to high frequent access. So we have our enriched logs, we have our normalized logs, and some other ad hoc files. We have our jar files for application files. We have some config files that are actually being used very frequently as well. And the location, we chose dual region. So we were considering, should we have two single region buckets or one dual region bucket? It's a little more expensive to go with the dual region choice that we made because it does auto data replication across both regions for us. So that handles some of the complexity of copying the data manually. So if you want to do two single region buckets, we do the manual copying, which is not preferred by us. Zero RPO is a key factor here because we need to ensure that our data is recoverable. For us, logs are actually worth money. Each click that we have made, we charge it to the sellers or the merchants. So we need to ensure that the data is not lost. We can recover all this data. And yeah, so that's on the standard side. And on our archival bucket, we store up to 2 years worth of data that is infrequently accessed, and both contains enriched and normalized logs. We chose single region more just to optimize on our storage costs. And yeah, we still get the required durability. And yeah, so the main type of files in our that we actually have to deal with, it's in terabytes. So it's terabytes of logs on clicks and impressions. Storage period average is about 3 months and is written by Dataflow. So in our system, we noticed that in the first 2 days, lots of access on these files, but beyond the 2 days, we don't access the files as much. And that's a consideration we have on the storage class, whether we want to move from standard storage to nearline after 2 days. Oh, sorry, cold line. So we can use the lifecycle policy for this. Yeah. And then BigQuery is a big part of our warehousing. So this is the analytics layer. This is where the reporting is done. This is where the querying is done. We use this very frequently. We chose BigQuery. It has some serverless features and scalability, meaning we don't handle infra ourselves. We just pay per query basis, and we are able to leverage our GCS data that's being stored. We're able to use that external tables to run the queries upon. So a couple of options. Actually, there are lots of options that were discussed in setting up of these BigQuery tables. So the first choice here is the BigQuery native table. So the native table actually requires us not just to have the GCS, underlying GCS data, but also have a batch load job running. So the load job will load the data from the GCS to the native tables. So this is the first option. The good thing about native tables, the query performance is really good. It's much faster than the rest of the options. And also being able to control access. We have lots of people accessing our data, our tables. We don't want one table to be accessed by everyone. Perhaps there's certain groups of people that need the access. So at the BigQuery table level, we're able to control the access without going into the GCS access. So only the BigQuery tables can be used to give the access to our relevant stakeholders. But the cons, like I mentioned, is the storage cost is extra because not only are we storing data on GCS, we also have a load job that loads native tables. So there's duplicated data. So that's a con that we actually weighed as well. Next option is our BigQuery external tables. So BigQuery external tables, it's cheaper because there's no load job. It's compared to native, there's no loading of data to native tables. We directly leverage our GCS data. So we are cutting on some cost. It's simple solution. From our side, there's less initial setup required, but the query performance is slow. That's the downside. But the queries, if you run a query maybe with 10 columns, but you're selecting only 2 of them, it will still scan through the whole file, all 10 columns. So this is a downside that we also noticed. And yeah, the biggest one is the access consideration. If you want to give access to people, stakeholders, the access is given on the GCS level, not on the table level. So no row level access, no it's harder to actually distribute access to a lot of our stakeholders. Lastly, this is what we prefer, actually the big lake external table. So after lots of testing and iteration, this is what we chose, big lake external tables. So similarly, it doesn't have extra costs on storing duplicated data. There's no load job running. We are only relying on the GCS data that's already been stored. So it avoids any additional storage costs. Also, access control easy. We can give BigQuery table access to maybe our travel team, maybe our fintech team, whoever needs access, we give them the relevant tables directly. The query performance is a little slow. We realize that for some of our use cases, we don't mind taking this con, but again, we are still under consideration whether this is a huge factor for us. But we optimize on cost, we optimize on access, the ease of giving access. So yeah, this is one of the cons that we have seen. So along this journey, actually, there's lots of things that we considered, but the two main considerations were actually the access control, like I mentioned, and also minimizing data duplication and data deletion. So if there's data duplication, if you have a load job running, what you can do is to minimize costs, because you have GCS stored data, maybe you have a native load job that runs you have a load job that stores data from GCS to the native tables. You have duplicated data. You want to minimize costs, you can delete the data after it's being loaded. But that gives us operational overhead that we want to avoid as well. So these are some of the considerations we have. Along with the different tables, actually, there's different file formats to consider. So there's different tables, but there's also JSON to consider, Avro, CSV, Parquet. Parquet is the more modern one that we were considering as well. But due to some of our heavy dependencies on JSON, so a lot of our upstream producers produce data in JSON. For us to migrate away from JSON to Parquet requires a lot of effort, because if the data is incoming on JSON, it's easier for us to store it in JSON rather than converting all of it to Parquet. And also we have published data for the last 2 years that maybe we have to consider, should we also, transform all of that data to Parquet. So there's a lot of considerations on this. Also the readability of the files. JSON tends to be human readable, easy to debug. Parquet, not so much. So that's another consideration we have on the readability of these data files. So when we do the testing also, we do different kind of queries to run. So if you want to see how much time it takes, how much cost the queries take, there's not just one query that we run all sorts of queries. And then we weigh upon those queries to see that which one works best for us. So which one has the least cost, maybe the fastest to run. So different file formats, different query types, different tables, all of these come into play when we're deciding our warehousing solution. So I'll pass the time on to Mankit to share more on our warehousing applications. Thank you.
Thank you, Raymond, for sharing with us the technicalities of our data warehouse, which is built on different GCP service components. Next, I would like to share more about our data warehouse use cases. The data that we store are largely ad performance data concerning the clicks, impressions, purchases, and all. And our downstream consumers use it mainly for two major use cases: analytics reporting and also machine learning. So let me give you some examples. So let's say an ad service would want to know like how many clicks and impressions for that day. They can aggregate it using our data to see how much all the metrics they are. Then we also identify some high performing items by sales volume. Then that would help us with some ad optimization. Yeah. There are also billing reports that can be generated from this data warehouse data, where we aggregate the GMS, total value of an ad campaign. Yeah, and then we will be able to bill the advertisers accordingly based on the sales. And we also have another dedicated team for the business intelligence dashboard, where they will ingest the data coming from our data warehouse into a data cube. And this will enable visualizations for our business users to see how the ad campaigns are performing across the different ad services at a glance, right? So next we have machine learning. There are some malicious users who will request our ads unnecessarily, creating large traffic on our ad servers. So for these cases, we will try to identify these users and maintain a blacklist of the IP and the user agent that you use. And when processing the logs, we will then label this click or impression logs as being fraudulent. Yeah, that part is on fraud detection. And we also have a data science team that analyzes the user activity, purchase trends of our other users to see which kind of products that they like, and then recommend ad items accordingly, generate a personalized list for them. Yeah, so these are just some of the applications that are possible. So we anticipate more of these use cases as teams get more data driven in onboarding new use cases or maybe strategic planning, right? So more users will be relying on our data, and it's important to be to get the data accurate and reliable. Yeah, so I guess this illustrates one of the common situations that we face. So data can be found in many places, right? And the table specifications, the situations on like say which scenarios to use which table from which team sometimes remain largely undocumented and is tribal knowledge. Yeah. So if we were to use and combine the data coming from these various locations, it's a bit precarious. You cannot guarantee the accuracy of the analytics report that you generate at the end. Cannot be confident of the numbers. Yeah. So we strive to be the data warehouse for a centralized data warehouse where the data is trusted by our users. So as what I've pointed out, one of the use case that we have earlier is generating the billing reports. So it's important that we get the amount right. Yeah. Otherwise, customers would lose trust in our brand. Yeah. So it's one of our key targets to maintain high data quality in our data warehouse. So I would like to share some of our practices to maintain high data quality within our data warehouse. So there is no one common standard to measure data quality. Yeah, here I'd like to focus on three key aspects when we design the data warehouse and also the operational processes around it. So that's relevance, accuracy, and timeliness. So for relevance, we only collect the data that has its fitting use case. We don't collect everything. So let's say an ad service is now onboarding releasing a new feature. So the system owners would come together and discuss how this new information will be stored and how it would appear in the final report. Yeah. So some of the discussion points would be like what would be the data type? Under one scenarios, would it take a certain value? What would be the default value, the null values? Would it impact other existing fields, so on and so forth? Yeah. So this would help us to achieve a normalized schema, a standardized schema. And as much as we'd like to store everything, there is a trade-off with storage costs because as what Raymond has pointed out earlier, we store hundreds of terabytes of data. So if we store everything, storage costs would be really high for us. So relevance would be something that is critical for us. So the next is accuracy. When we process the data, we ensure that the critical fields are there. And after processing it as well, we check in both the source and destination, do a comparison to ensure that nothing gets lost in between. Yeah. So this helps us with detection of any kinds of issues. So if there are, then our orchestrator will raise an alert and our engineers will take a look at it to see what is the problem. And if there is a system issue, be it in our pipeline or in the upstream systems, then we will try to follow a set of recovery procedures. So say we are going to republish the data again into Kafka or reprocess the data into GCS, for example. Yeah, and this needs to be done in a certain time frame. Yeah. Oops. Should be moving forward. Yeah. Yeah. Next is the timeliness of data. So as a data platform, we have many users relying on us to run the jobs on time as well. So we have service level agreements defined to ensure that the data is available at what time frame. Yeah, if there is a certain issue and there's an alert, so our engineers are constantly on call on a rotation basis to handle the alert within that designated time, hopefully within the SLA timeframe. Then this will help us to avoid service impact that happens downstream. Of course, there can be many other data quality dimensions that we can talk about. Some of them belongs more to a data architecting level, but for today's discussion, I think at the operational and data engineering level, I think this is what's suitable to share here. Yeah, so I think that concludes the data warehousing portion of our sharing today. I hope this gives you some tips if you are building or in the process of migrating to a data warehouse. So I'll maybe move on to a Q&A session. If you have any questions, feel free to ask, or if you have any suggestions on like say possibly some discussion points of what we have shared earlier, yeah, feel free to discuss as well. Thank you. Oh, okay, right.
So just a question on the link and data flow. So since both link and data flow are doing real-time testing, I know like a lot of services you guys are migrating to I would assume like currently you are some of very going to use something in GCP to replace your thing setup, and since both link and the data flow are similar stuff, how do you guys choose like under what use cases or scenarios?
Yeah, as we are migrating to the cloud service, we are keeping our Flink application. So we will be consuming it from the data source, and we will use the Flink application to process, filter, and transform. But where we publish has been changed. It would be to the PubSub. And we are using the data flow to consume from the PubSub in a batch manner and write it to the GCS. Yeah. Thank you.
And also another thing to point out is that data flow runs on is Apache Beam, which runs on a higher level API compared to Flink, right? We want more control on our streaming pipeline, which is running on data streams. Yeah, so we want more control over it. So I think unless we would want to work on a higher level, I think we would stay with the current Flink choice of Flink that we currently have. Yeah.
Hello. I'm Aaron from Rockler team. I want to ask that from your data proc, are you running the Spark jar or Spark Circle?
What's the second one?
Spark Circle or Spark jar?
Oh. We create the jar file. It's a Scala application that we built and do a data proc submit to process the data from GCS. So why we choose a Scala application jar instead of SQL is that we can write unit tests for the various transformations that we have. Then yeah, this would help us to test our application. It will be hard to do that at a SQL level. So this is one of the advantages that we want.
Then the does dataproc support if you start a Scala shell and execute your Scala code one line by one line for debugging purpose?
That part I can answer. I think I've looked into that part as well. I think the Dataproc has different offerings. There is Dataproc on GCE, which runs on a cluster of virtual machines. There is Dataproc on Kubernetes, Dataproc serverless. So all these would offers a REPL the shell kind of interface. So we have tried for GCE. So once we spin up a Dataproc cluster, which is essentially a Hadoop cluster, we are able to SSH into the master node and get access to the Spark shell. So there you would get what you're familiar with, which is the Spark shell where you can run Spark commands interactively. I think that would be quite similar with Dataproc on Kubernetes as well. So there is this new offering from Dataproc, which is Dataproc serverless. So instead of managing the virtual machines, you just define however many executors, how much RAM or CPU cores that you want in your executors, and all these containers would be managed by Dataproc themselves. So you don't have to manage any servers. So for this one, you don't actually get a Spark shell. So from GCP, they have a particular workflow to access this interactive. It's called interactive sessions. So for that, you need to spin up some interactive session, which can be accessed via a Jupyter notebook. So these are the various ways that you can get a Spark interactive shell on Dataproc. So depends on which kind of product offering that you use for Dataproc actually.
Hi, could you share on your strategies for dealing with slowly changing dimensions? So, for example, let's say a certain product undergoes a name change, or perhaps like a certain attribution formula has changed. So, how do you deal with that?
Attribution schema.
Yeah, like you guys do like a backfill.
So far, we have not encountered that where okay, so when there's a new field, then the past history for us would be all null values. Yeah, so the downstream users will only be utilizing the field when it is first after it has been introduced. So far, I haven't seen like past columns being changed into new ones. Have you?
Sorry, again, can you repeat your question? Is the schema changed to the data that they publish, is it? So it would come like a request. So when you would be changing your schema, when you think the existing field is not enough and you would need more fields to make an analysis or to optimize your business, so they would make it as a request. So we would get from our BU people, and we would see what type of field they are requesting and what is the data type that we are going to get in. Then we would change the schema and do some internal testing. Then we would be releasing it in the production to inherit the particular field that is coming in. So it always goes through this process. We don't consume whatever fields they are publishing. We have a set of schema, so we only consume those set of fields. And if they want to ingest a new field, they make it as a request and we make the changes in the schema. Yeah. Yeah, right. Yeah, exactly. And if there is any error logs, we are writing it to a different Kafka topic for our analysis purposes, like how much error data we are getting and from which service we are getting it.
Can we actually use AWS instead of GCP? Like for this setup?
Actually, yes, you can. But here in Rakuten, we have adapted to the GCP. So we haven't much investigated on the AWS. Sorry, maybe.
Yeah, I'm sure there's equivalent services.
Equivalent services, but here we have adapted for the GCP.
Okay.
Yeah.
Okay. And my second question is, oh, now I lost my train of thought. Maybe come back later.
Sure.
Maybe I got a question. Yeah. Okay.
I remember. Thank you. Can I know how much that you actually spend? I mean, with the current setup with on-premise before you actually go to GCP for this, how much you already spend on these things, Kafka, Flink? And then maybe my follow-up question is, how much is actually changed when you actually move to GCP? Like how much you spend more or maybe less? Yeah, just cause estimation. I just want to know. I mean, on-premise versus the cloud thing. So. Oh, or confidential. I'm sorry. If-
Actually, I want to ask the same question, but it's sort of answered. Yeah, I wanted to ask another question is about your data retention. So how long do you guys retain your data? Is there like some life cycle? Yeah.
So actually, the data retention of each team depends upon your stakeholders, like who is consuming your data. As Rahman has shared, we have this hot data and the cold data. So the recent 3 months of data, we store it in the normal path because that is where we get number of queries and reports being generated on that data. And the remaining data, more than 3 months, we store it in the archive. We do that in Hive to optimize the table performance. So if you have so many partitions in a table, then it would lower the query performance. So we had that setup. But moving forward to the GCS, the cost also matters. So we have the standard storage for the 3 months, and the rest would be the archive storage because the cost of the archive would be comparatively like way more less than the standard storage. But again, we always get agreement from our stakeholders for the retention period that we don't store more than 2 years of data.
Okay, 2 years. I see.
Yes.
What about machine learning scenarios? Do you
Machine
store?
learning
Yeah.
scenarios.
Do you also store 2 years of data for train your models, or it varies? Yeah.
Oh, actually, we have one group called the ad optimization group where they go through the history of data to observe the user patterns, and then to the items they have purchased, they would be applying some logics to optimize the ads and all that. So they also use 2 years of data, but that's again agreement within Ultra. When you go to other teams of Rakuten, they might have a different agreement according to their stakeholders.
Okay, thank you.
So when you're streaming the data, did you do a comparison with after you collect the data in batch, you compare the data is streaming and the data from the batch? Is there any difference?
um, the comparison between the streaming and batch, is it? So actually, the application where we use the streaming and batch differs. So some of the stakeholders might demand for the real-time data. So those services, we process it in the streaming. And some of the services where they don't need the data in real time, it is enough for them to consume the yesterday's data with a particular SLA. Like for example, today 12, PM, everything should be available for yesterday's date. So those kind of data, we process it in the batch. So we don't process the same data in streaming and batch. The data we are processing is different for streaming and batch. But we always compare the source, yes. Yeah, if you ask how we are making sure that we consume all the data, we compare it with the source after some time. Yeah, of course, not in the real time. We cannot compare it.
Any more questions? I guess no. Okay. Right. Okay, then I think we can wrap up today. Yeah. Any things you want to close? Or
No closing actually, but if other if other attendees have any like questions that would want to consult us personally, feel free to do it after this session also. Yeah, we'll be staying around for a bit. Yeah, maybe we can network and discuss a bit.